Welcome to Chapter 4's lecture on chemical bonding. In this chapter, we're going to be covering the different types of chemical bonds and their nomenclature, and then move into Lewis structures and electronegativity, and then looking a little bit deeper into how Lewis structures are drawn and what they represent. So looking at the different types of chemical bonds we have, so you can think of the formation of a compound. It's between individual elements, and it occurs in order for those elements to become more stable. So atoms are linked together by their chemical bonds in order to lower their energy states. In general, there are three types of chemical bonds. So there's the ionic bond. In an ionic bond, there's an electrostatic attraction between a positively charged particle, the cation, and a negatively charged particle, the anion. In most cases, these ions are formed by the transfer of an electron from a metal to a nonmetal. And these electrostatic forces that occur that are holding the cations and anions together, they hold them together in the form of a crystal lattice. So we don't talk about ionic compounds in terms of molecules, we talk about them in terms of their lowest formula unit, their lowest ratio in that crystal lattice. Covalent bonds, that happens when two nonmetals combine. They share electrons in their valence shells. And then the third type of chemical bond we have metallic bonds. And so that occurs in a solid metal. And the electrons are highly delocalized. They kind of form this sea of electrons that move freely among all the metal atoms in that metallic solid. The free movement of electrons explains the good electrical and thermal conductivity of metals. Okay. Taking a closer look at covalent bonding, take a look at this sentence, try and fill in the blanks, pause it if you need. So molecular compounds are substances that are formed when nonmetals combine by sharing electrons to form covalent bonds. So these nonmetals are forming in such a way so that each atom contains that noble gas configuration with 8 valence electrons. And the distance between the atoms when energy is at a minimum, that is called the bond length. So in this diagram, this is showing the electrostatic potential energy of electrons in a covalent bond for a hydrogen molecule. Okay. So you can see the free hydrogen atoms on the far right before they start bonding, and they experience little to no electrostatic attraction because they are too far apart. Then as the hydrogen atoms move closer together, they begin to experience these attractive forces. The negative electrons are attracted to the positively charged nucleus of the other atom. The closer the atoms are in space, the greater that electrostatic attraction becomes. The potential energy decreases as it is converted into these electrostatic attractive forces. Beyond a certain point, however, you can see that the two atoms begin to experience repulsive forces, and this is because of the proximity of the positively charged nuclei. And so at that point, when the two nuclei become too close, the potential energy starts to increase again. So the distance at which the potential energy is at its lowest point, i.e. the greatest attractive energy, that's called the bond length. It's 75 picometers for hydrogen bonds, and the energy minimum in the potential energy curve is represents the hydrogen bond energy. Let's see, that one is negative 432 kilojoules per mole. So the energy released when 2 moles of hydrogen atoms combine to form 1 mole of hydrogen molecules would be 432 kilojoules per mole. So you would have to provide this much energy to break the bonds in a mole of hydrogen molecules in order to free those hydrogen atoms. And you can see those values on the graph that I indicated there. So recapping our types of chemical bonds and their properties. Okay, you've got ionic bonds. They're characterized by transfer of electrons, usually between a metal and a nonmetal. In this example here, you have your sodium atom transferring an electron to a chlorine atom to form a sodium cation and a chlorine anion. Those oppositely charged particles are then held together in this three-dimensional crystal lattice, which you can see illustrated there, and it's just alternating the positive and the negative charges. Covalent compounds, those are created by sharing electrons, typically between 2 nonmetals. You can also have metalloids involved in these. And so this sharing of electrons results in the formation of these discrete molecules. So here in this picture you can see 2 bromine atoms combining to form a bromine molecule, and that's just a discrete molecule, unlike ionic compounds where you have the crystal lattice. And metallic bonds, those are metal nuclei that are held together by this pooling of loosely held electrons. So there's a sea of electrons surrounding those nuclei involved in that metallic bond. So the next section looks at the nomenclature of these different compounds. So first we're going to start out with looking at ionic compounds and just binary ionic compounds, which means only 2 elements are involved. So ionic compounds consist of ions, positively or negatively charged particles, and they're held together by electrostatic attractions. Ionic compounds generally consist of a metal combined with a nonmetal. And in binary, 2-element ionic compounds, the ions are formed by the transfer of 1 or more electrons from the atoms of one element to the atoms of the other element. As a general rule, metal atoms tend to always lose electrons to form the positively charged cation. Nonmetals tend to gain electrons to form negatively charged anions. So then those opposite charges are held together by these electrostatic forces, and we call that an ionic bond. The simplest whole number ratio of cations to anions that yields a neutral compound, that is what we call the formula unit. So metal lose electrons to form cations, whereas nonmetals gain electrons to form anions. The number of electrons gained or lost depends on the location of the element on the periodic table. We can then use the periodic table to help us predict the chemical formula of ionic compounds. So group 1 metals, they lose their 1 valence electron to form cations with a +1 charge. So you've got sodium, which makes a +1, potassium makes a +1. Then there's group 2 metals. They lose 2 valence electrons to form the cations with a +2 charge. So you've got magnesium has a +2 and calcium has a +2. The nonmetal elements, those gain electrons to form anions, and the total number of electrons gained can be calculated using group 18, for example. They all want to become like group 18. So the halogens, which is group 17, they're always going to gain 1 electron. So you got fluorine -1, chlorine -1. The groups in this group 16 elements, those are going to gain 2 electrons. So you've got oxygen, which makes a -2, sulfur makes a -2, and so on. So elements tend to gain or lose the number of electrons that will result in the atom having the same number of electrons as the closest noble gas. And the relative number of cations and anions needed to produce a neutral compound determines the formula unit. So, for example, the most common example used is always sodium and chlorine. So those would combine in a 1-to-1 ratio because you have a +1 sodium and a -1 chlorine. So that would produce the formula unit NaCl. Okay. Looking at one that's a little bit different, magnesium and chlorine, those form a magnesium +2 and a chlorine -1. So we would need twice as many chlorine ions to maintain a neutral charge, or a formula unit of magnesium and 2 chlorines. So that would look like what we have here. So that would be our formula unit. Okay. The charges on ions in these main group elements, they are easy to predict based on their position on the periodic table. However, charges on transition metals can vary. For example, a sodium ion is always +1, but an ion of iron can be +2 or +3, and an ion of copper can be +1 or +2. So when naming binary ionic compounds, you start with the name of the cation. We'll use magnesium chloride for our example. So you start with the name of the cation, so magnesium, and then you add the name of the anion, modifying the name of the element at the end by adding the suffix ied, so that we get ide. Okay, so chlorine becomes chloride. So we have magnesium chloride, and that's how we would say this, this compound. So note, we call these kind of compounds type 1 compounds, okay, because the charges on magnesium and chlorine are already well established based on the position of their periodic table. Okay, because the name and formula must correspond to a neutral compound, there is only one possible formula that will be neutral, MgCl2. So numerical prefixes are not needed for ionic compounds involved in group 1 or group 2 metals. Or other metals, there are some special cases that classify as these type 1 compounds. So when you don't need, basically when you know that they're always going to make the same sort of ion, they're considered a type 1 compound. Okay, other exceptions to this are going to be zinc. It's in the transition metal groups, but zinc always makes a +2 ion. Aluminum, that's a group 3 or group 13, so just remember it always makes a +3, but it follows the periodic table trend. Other ones, so we've got silver, that always makes a +1. Gold also always makes, I believe, a +2. So those are some metals that get grouped as these type 1 compounds where you don't need to make any other notations because they always make the same cation. So we call those type 1 metals. For type 2 metals, so when I refer to an ionic compound that's a type 2, okay, that means that I'm talking about a transition metal or other metals that can have more than one possible charge. Like lead can have a +2 or a +4. Lead technically is not in the transition metal group, but it does have the different ions. Okay, so the charge on the cation must be specified when naming the compound. So when we need to specify the charge on the cation, we use a Roman numeral, which is inserted into parentheses after the name of a metal to indicate its charge on the cation. So let's use iron and chlorine as an example. Okay, so here we've got FeCl2. So in that case, when we have that formula, Okay, when we go to write the name, we know that iron must be a +2 so that the compound is neutral. So we write that out as iron Roman numeral 2 chloride. Okay, when we have the formula FeCl3, we know that iron must have a +3 charge. So we write the compound iron Roman numeral 3 chloride. So before we had this naming system, we used some other ways of telling the difference by using Latin roots. So we used, for iron, we had the ending us or ic to represent the different ions. So the naming would change. So we had the us ending, and so that suffix was added to the ion of the lower charge, while the ic ending was added to the ion of the greater charge. So iron 2 chloride was known as ferrous chloride. So that's something that you might see in your textbook or other readings. And so then iron 3 chloride would have been ferric chloride. This comes from Latin. Ferrium means iron, and so that's why iron is represented as Fe on the periodic table. So when you hear me talk about a type 2 ionic compound, I'm referring to when you need to indicate its charge with a Roman numeral because it has variable charges. Okay, so you've got type 1 metals, which always make the same ion, and you have type 2 metals, which make different ions that you need to denote with the Roman numeral. Okay, so you're going to do some practice on the next slide for this. Okay, work through these, pause this, and then tune back in for the answers to check your work. So the first thing I always recommend when you start naming is you identify the metal as a type 1 or a type 2. So sodium is a group 1 ion, so that always makes the same type of ion. So that's going to be a type 1 compound. Chromium, okay, that's in the transition metal family, so that probably is going to have some other ones. I think through my special cases, and so I realized that this is going to be a type 2 ionic compound. Okay, down here we have zinc and copper. Zinc, remember, it's going to be one of your special cases. It always makes a +2 ion, so this is actually going to be a type 1 compound. Okay, and then copper, okay, I know it has different ions, so this is going to make a type 2 compound. Okay, so I've got them identified, so now I can follow my naming rules. So when writing formulas or naming ionic compounds, remember the cation is always written first, and the name is simply naming the element. The anion is written second, and the element name is just modified by adding the IED suffix. Okay, changes on anions and cations can usually be determined based on if it's a type 1 or a type 2. So type 1, you're not making any other additional changes. Type 2, you need to indicate the charge of the ion, the cation. So for type 1, I just name the cation because it always makes a +1 charge. Okay. And then the anion, that's going to be bromine. And so we change the ending to "ide." So bromine becomes bromide. Okay, in B, okay, first thing, you always write the metal. So we have chromium. And then because it is a type 2, I know I'm going to have to indicate the charge. Okay, so I'll do that after I write everything else. And then chlorine is the anion, so you change the ending to "ide." Chloride. Okay, then what you need to do is you need to figure out what the charge is going to be. You know that chlorine makes a -1, and you know that you have 3 of them. Okay, so that's going to give you a -3 charge. So in order to have, so you have a -3 charge that needs to be balanced out. So that means that chromium must be +3, okay, in order to balance the charge out. So that gives you Roman numeral 3. Alright, so for zinc nitride, you know zinc is a type 1 metal, so it always has a +2 charge. Okay. Nitride, which means nitrogen, so you've got nitrogen, you look at your periodic table, and you see that it's going to make a -3 anion. Okay. So you've got zinc at +2, nitrogen at -3. You need these to equal 0. So you're going to I do a little equation like this, and I see I want this to equal 0, so now I need to figure out what those numbers are going to be. And I see that the lowest ratio, so if I have 2 nitrogens and 3 zincs, that gives me +6 and -6, which equals 0. So then I go to write my formula. I've got 3 zincs and 2 nitrogens. Another way that you can think about this, you may have learned this shortcut. So you've got zinc +2 and nitrogen -3. So writing the skeleton structure for this, you've got zinc and nitrogen, and then if you just cross their charges, so the -3, you take the charge off, and you just put 3 here, +2, take the charge off, and put the charge, so you're just crossing them. So that goes here, and that goes down here. Okay, so that's one method that you can also look at. So then copper 1 oxide, so we've got copper, which is a +1 ion based on its Roman numeral, and oxide, which means oxygen, and oxygen, looking at the periodic table, it has a -2 charge. Okay, so whatever method works best for you. So you've got, let me see, let me give myself some more space. So we want these to equal 0. Alright, so we've got a +1 and a -2. So if we have 1 -2 charge and 2 +1 charges, 2, that gives us a total of +2, a total of -2, which gives us 0. You could have also done the cross method. Let's see, let's use red. Okay, so colors so that you can follow along. So we've got copper and oxygen as our skeleton, and then to figure out their charges, you just circle the charge there and drop it down to copper. So you're going to have 2 coppers, and take the 1, drop it down. So that also tells you you're going to have 1. You don't need to write the 1 is assumed. So either way, no matter what method you do, you see that you've got Cu2. Oh, and that is going to be your molecular formula. Excuse me, your formula unit. Molecular formulas are for covalent. This is an ionic compound, so this is our formula unit. Okay. All right, so we looked at binary compounds. We can also make ionic compounds using these polyatomic ions. And polyatomic ions are groups of atoms with more than one element joined together. So these polyatomic ions, they're joined together covalently, and then they have an overall positive or negative charge. The only 2 common polyatomic cations are ammonium, so ammonium is NH4+1, and hydronium, which is H3O+1. Okay, most common polyatomic ions, they contain an oxygen combined with other atoms and are called oxoanions. Okay, so most of your polyatomics fall under this category. And so unlike monoatomic ions, okay, these polyatomic ions are not, their naming is a little non-intuitive. So overall, you usually just memorize the names, formulas, and charges of common polyatomic ions. So in your book, there are a list of polyatomic ions that I expect you to know. That's on page 142 in your textbook. Okay, there's some examples here. So when you are forming ionic compounds and you're only using monoatomic atoms to make monoatomic ions to make these compounds, you're always using the end of IDE. You're using IDE. But you'll notice when you work with polyatomic ions, okay, it's not that simple. So you just take polyatomic ion and you just write its exact name. Okay, most of the time the suffixes are going to end in ate or ite. So a couple of examples you can see here, and then look to your textbook for the list of the rest of them. Okay, and so overall, I expect you to know that whole list that's on that table. If I expect you to know any more beyond that, I'll probably specify or give it to you if it's something that was not on this list. And on an exam, I would give you that name. Okay, here's some practice with using polyatomic ions in the namings. Go ahead and pause and then tune back in for the answer. Alright, so looking at this, chromium, that's a type 2 metal. Okay, NH4 here, that is a polyatomic ion. And so because a polyatomic ion, all you do is state the name of the polyatomic ion. It works just like a type 1. Okay. Down here, lithium, that's a type 1 metal, and calcium is also a type 1 metal. Okay, so then we go to name. So first thing you do is you always just write the name of the metal, or the positive ion. So we've got chromium, okay, and then for the anion, you look at that, you see it's a polyatomic ion. Let's see, and we're going to have a charge, but we'll worry about that later. And you see on your table that ClO4 is a -1 ion, and its name is perchlorate. So all you got to do is name perchlorate. Okay, at this point, then you need to backtrack and try and figure out the charge of chromium. So you know that ClO4 is a -1. Okay, you want this to equal 0. And you know that you have 3 of them. Okay, right there it tells you you have 3. Okay, and so we want to know what the charge is on 1 chromium. So what is chromium's charge? Okay, so you've got 3 -1 charges. Okay, so you have a total of a -3 over here. So that means this needs to be +3. And you have 1, so you know that this is going to be Cr +3. Okay, so then you give it Roman numeral 3. Okay, moving on to the next one. You can see that's 2 polyatomic ions combined. So the cation is named ammonium. So when you have polyatomics, all you have to do is name ammonium. And then NO3, that is nitrate. So then you just name nitrate. Alright, so going down to lithium bicarbonate. So lithium, you write lithium, and lithium is a +1. And bicarbonate, so you gotta look that one up, but you're going to be memorizing that. And so bicarbonate is HCO3 -1. Okay, so it's a +1 -1, so they're a perfect ratio. So you don't need to think about how many of each you need, you just one of each. So you've got lithium and bicarbonate. So that's going to be HCO3. You've got one lithium, one carbonate. That is good to go. All right. And then the last one, calcium hypobromite. So calcium is a +2. Hypobromite is BRO -1. Okay. So again, you can do this using either method. And you see that you have one calcium, you're going to need 2 hypobromites. Okay, so writing this out, you've got 1 calcium and 2 hypobromites, and that will give you a neutral charge. Okay, so that was a good rundown of naming ionic compounds. So moving forward, looking at covalent compounds in molecules. Remember, this is 2 nonmetals bonding together by sharing electrons to form a covalent bond. We're mostly going to focus on binary compounds, so just 2 different elements combining together. And so your difference here is that atoms are combining to form these discrete molecules with definite compositions. So the ratios are exact, and that's a specific molecule, versus ionic compounds are forming those complex crystal lattices that then just have the lowest ratio as our formula unit. So here we're looking at discrete molecules. The composition of a molecular compound is represented by a molecular formula versus a formula unit in ionic compounds. So a molecular formula shows the number and types of atoms present in one molecule of that compound. So for H2O, that means it consists of 2 atoms of hydrogen bonded to 1 atom of oxygen. A molecule of SO3 contains 3 atoms of oxygen combined with 1 atom of sulfur. So a molecular formula is different than an empirical formula. And so what an empirical formula is it shows the smallest whole number ratio of elements in a compound. So for example, the molecular formula for glucose is C6H12O6, which would be different than its empirical formula. So glucose is C6H12O6. Okay, and that's its molecular formula. Okay, its empirical formula, okay, is just reducing those whole number ratios to produce, we would get, let's see, it would be CH2O. And this would be glucose's empirical formula. Okay, we're going to look at empirical formulas in our lab. So at this point, let me get out of this, there we go. So at this point, we can identify compounds as molecular or ionic based on their chemical formulas, so looking at the elements involved. And the names and formulas of these different compounds are basically what we use in everything moving forward. And so we need to pay really careful attention of the rules for naming these compounds. Overall, the periodic table helps us out a lot in naming these. So looking at just these simple binary molecular compounds, which just have 2 nonmetals joined by covalent bonds, we have rules for naming. So first thing, you start with the name of the first element in the formula. This is usually going to be the element that's farther to the left on the periodic table. Or if the elements are in the same group and family, then it's going to be usually the element with the higher atomic number goes first. Okay, so in SO3, so sulfur, okay, would go first because it has the higher atomic number compared to oxygen because they're in the same family. The name of the second element is modified by adding the suffix IDE, so "ide" at the end. So for oxygen, we'd be changing it to oxide. And then lastly, we would use prefixes to indicate the number of atoms of each type. So for SO3, the first element is sulfur, okay, the second is oxygen, and it becomes oxide. But because there are 3 oxygens, we're going to have sulfur trioxide. And so these prefixes, to indicate how many there are in your book on page 143. Okay. So here's that table with those prefixes. Overall, when you're using the prefix mono, you never include mono when it's the first element. You only include mono when it's the second element. So like H2O is dihydrogen monoxide. Okay. There's also a couple of certain situations. So when you have prefixes that end with an O or an A, okay, they get modified when you're using elements that start with vowels. Okay, so decaoxide would become decoxide. Monooxide becomes monoxide. So you lose that first vowel of the element. So acids are also included in talking about nomenclature, and they're substances that have very specific chemical properties. We'll be looking at them later on in different chapters, but they're most characteristic for releasing hydrogen ions when dissolved in water. And because of these special behaviors of acids, we have a separate set of rules to name them. Okay, so a binary acid we're going to focus on mainly, that just contains a hydrogen and then one other atomic ion. So either chlorine or sulfur or any of those negative ions that can combine with a hydrogen. Okay, oftentimes it's the halide ions. So when naming a binary acid, okay, so we're going to be using the prefix hydro to indicate the hydrogen portion of the acid compound. Okay, so here's a couple examples. Okay, there we go. So we're going to be using the hydro prefix to indicate the hydrogens, and then the anion base is used, and you change the end to "ic." Okay, and then you just add the word acid. So you got hydro, and then you list the halogen involved, and you change the halogen's name to "ic" at the end, and then you add acid. So for example, you've got HBr is hydro, and then bromine changes to bromic, and then you add acid. So hydrobromic acid. Another example, H2S, so that would be hydro, and then it's combining with sulfur, so hydrosulfuric acid. When naming polyatomic ions involved in acids, there are some rules for that as well. So the oxo anions will all form acids with hydrogen. And so you'll see that there are several possible combinations of oxygen in their elements looking at your polyatomic ions. And they have the endings of "ate" or "ite." So when they form acids, they traditionally change those endings. So if you have a polyatomic ion that ends in "ate," okay, when it forms an acid, you're going to change the "ate" to "ic." If you have a polyatomic ion that ends in "ite," when it forms an acid with hydrogen, it'll change from "ite" to "ush," and then add acid at the end. Okay, so hypochlorite becomes hypochlorous acid. So a side note here, looking at your polyatomic ions, trying to make sure that you're able to memorize them, you'll look and kind of notice a pattern in these names for these oxoanions. And so the oxoanions typically do form kind of a pattern in their naming process. Okay, so if you look at that, you'll notice it goes hypochlorite and then chlorite, and then it changes to chlorate and then perchlorate. And so this is a pattern that you can apply to other groups of polyatomic ions. So we have the suffix "ite" and the suffix "ate. And so those indicate the relative number of oxygens. So if there's only 2 common polyatomic ions for that oxoanion, okay, then the "ite" suffix applies to the one with the fewer oxygens, and the "ate" suffix applies to the one with the greater number of oxygens. So like nitrate has 3 oxygens and nitrite has 2 oxygens. SO3, so SO3 is sulfite and SO4 is sulfate. Okay. Halogens, on the other hand, so halogens can combine to form more than 2 common oxoanions. So we add in the prefix hypo to indicate that there is 1 less oxygen, and the prefix per to indicate that there's 1 more oxygen. So hypochlorite has 1 less oxygen than the chlorite ion. Okay, and then the chlorate ion, you'll notice there has 3, and when we say perchlorate, we're adding 1 more oxygen onto the chlorate. Okay, so that might be a good trick to help you memorize all the polyatomic ions that are expected. Now for a practice problem. Okay, so take your time, read through this, go ahead and pause, and then tune back in for your answer. I'm just going to write out all these answers at once, and so that'll show up in 3, 2, 1. So here are your answers. If you need a little bit more help with this problem, if this problem presented a lot of challenges, please make sure you're coming into office hours, and I can absolutely give you some tips and tricks for helping in naming and nomenclature. Okay, so that's a good combo, good test of your knowledge of this stuff. So then moving on from our nomenclature, okay, we're going to move on to Lewis structures. So in 1916, a guy named Gilbert Lewis proposed that atoms form chemical bonds by sharing electrons. So this proposal, it was before our quantum mechanic model, so it's a little outdated, but it still provides a very useful working model of how atoms form bonds. So in this section, we're going to discuss Lewis structures, which are just a model for representing the distribution of valence electrons in individual atoms and in compounds. So Lewis proposed that atoms form bonds by sharing electrons to acquire the stable electron configuration of a noble gas. Today we associate this electron configuration with completely filled s and p orbitals in the valence shell. So Lewis coined this whole idea as the octet rule, which states that atoms tend to gain, lose, or share electrons to achieve 8 valence electrons, or an octet. So using Lewis symbols, we can represent the distribution of our valence electrons in the atom. Okay, so the nucleus is represented by the symbol for the element. So for example, if we had C for carbon, and then the valence electrons are represented by dots distributed around the symbol. So when you go to place the electron dots, the first 4 electrons are unpaired and placed anywhere along the symbol, so on the top, sides, or bottom of the symbol. And then the additional dots are then added to form pairs until the valence shell is filled with 8 electrons. Okay, so you can see here sodium has one valence electron, so that dot could have been on top, bottom, or either of the sides. And then magnesium, as long as those electrons are not paired, they can be anywhere around the symbol. So what you can see here are the Lewis dot symbols for the main group elements, so groups 1, 2, and 13 through 18. Notice that all the elements in the same family have the same arrangement of dots because they have the same valence electron configurations. Okay, so for example, if you look at group 1, all group 1 elements have one dot. Group 2, they all have two, and so on. So remember that when you have two nonmetals, they share electrons. So unpaired electron dots here could also represent the ability for nonmetals to form covalent bonds, or the bonding capacity. Okay, so if you look at carbon, carbon has 4 unpaired dots. That means that carbon can form 4 covalent bonds because it has 4 unpaired electrons to share. And so members of each family exhibit similar bonding capacities. So in carbon, all the members of carbon's family can form 4 bonds. So not all elements will follow our octet rule. Many can form compounds with one or more atoms that are actually even electron deficient. Some can form expansions. So we'll take a look at some exceptions to the octet rule further down in section 8. When writing Lewis structures for ionic bonds, remember that that is 2 ions that come together with electrostatic attraction. So when forming an ionic bond Lewis structure, you're actually completing the octet for the negative anion and then making the positive ion, which doesn't have any more valence electrons. They've all been sucked away. So you can see that illustrated here. So sodium transfers its electron to chlorine. So then chlorine's structure is listed there. You'll notice because it's an ion, we often have these brackets. This is going to come into play when we do Lewis structures for polyatomics. You always want to remember to put the bracket around any ion and then add its charge on the outside there. Okay, looking at molecular compounds, okay, you can see the example here. So this Lewis structure is a two-dimensional representation of the molecule, showing how atoms in the molecule are connected. So pairs of electrons are shared between two atoms to represent the covalent bond, which can be shown as the straight line connecting the atoms. Okay, so you see the straight line between hydrogens and oxygen. Okay, one pair of shared electrons is called a single bond. And then pairs of electrons that are not shared, so those dots above and below oxygen, those are called lone pairs, meaning they're not involved in a bond. So there's a lot of different ways out there to talk about how to draw a Lewis structure. Overall, most of them use a 5-step approach. So in that approach, okay, the first step is to determine the number of valence electrons. For a neutral molecule, you just count the valence electrons for all the atoms in the molecule. If you have a polyatomic ion, you have to add or subtract electrons to account for the charge on that ion. And then the total number of electrons will be used to form the bonds in the lone pairs in the Lewis structure. So then your next step is to arrange the symbols for the atoms in a pattern that shows how their atoms are bonded together. And then you connect them with a single bond, and that single bond represents a pair of bonding electrons. The atom with the greatest bonding capacity is usually going to be your central atom. And those that form the fewest bonds, so like hydrogen, those are always arranged on the periphery. Okay, so think about bonding capacity to help you figure out which one will go in the center. Recall that bonding capacity is the ability of nonmetals to form covalent bonds. So it's usually represented by the element with the most unpaired electrons. Also, the element with the highest bonding capacity is usually listed first in the formula. So at this point, you should have something that I refer to as the skeleton structure. And you're ready to start filling in the remaining electrons. So you start completing the octets around each peripheral atom by adding lone pairs until each atom has a complete octet, or until you run out of valence electrons. So then you compare the number of electrons in the structure to the initial number of valence electrons determined in step 1. If there's still electrons left over, then you add them as lone pairs onto the central atom. Okay, so then you complete the octet around the central atom. If the central atom has an octet, when you finish step 4, you're done. If the central atom has less than an octet, then you need to create a double bond between a central atom and one or more of the peripheral atoms, using the lone pairs of electrons from those peripheral atoms. So Lewis structures can show bonding in molecules in which two atoms share more than one pair of electrons. So this double bond is that sharing of two pairs of electrons, and you just represent it by that double line. And then you can also have a triple bond, and that's the sharing of three pairs of electrons, and it's represented by those 3 lines between the atoms. Typically, we find out if a molecule has a multiple bond in step 4 and 5 of the Lewis structure process. When we run out of valence electrons, as we're counting and we're going, we suddenly don't have enough valence electrons. That immediately tells you that your central atom needs a double bond on it. So putting these rules into practice, go ahead and draw the structure for magnesium fluoride. Go ahead and pause and then tune back in for the answer. So this compound is a little tricky because it is an ionic compound. Okay, so magnesium is a group 2 and it has 2 valence electrons. So we're going to need to transfer both of those electrons, okay, over to fluorine. So magnesium is going to donate one of their valence electrons to one fluorine and one of their valence electrons to the other fluorine. Okay, and so that will result in magnesium being a +2 ion. Okay, and then each fluorine is going to gain 1 electron, so it's going to become a -1. And so at this point, magnesium has 0 valence electrons, and fluorine now has 8 valence electrons each. So writing the Lewis structure for this, okay, magnesium has no valence electrons, so it just gets the +2 charge. And then we have 2 fluorines, and so fluorine has 8 electrons. So we fill it in clockwise and then pair. And it has a -1 charge. So notice how we use the brackets. And so this would be the overall Lewis structure for an ionic compound of magnesium fluoride. For covalent compounds, you have 3 structures here to practice with. Go ahead and pause and then tune back in to check your work. So in answering this question, I'm going to show a table with the overall answer, and we'll go over the structures from there. Okay, so here's your table. for the 3 different compounds, and so this is giving you the total valence number of electrons. Remember, that's step 1, and then analyzing it, thinking about what is going to be the central atom, and then the process of going through and drawing them all. So pause, consult this, compare your answers, and then I will put up the actual Lewis structures here in a second. So you can see the Lewis structures down here. Notice that the Lewis structures are only concerned with the placement of electrons. These structures are not written in a way to represent the actual shape or the geometry. Okay, so those are done separately. The molecular geometry has different ways of being drawn. Lewis structure is just one form of a model of an atom, and its focus is only on where the electrons are. Okay, so hopefully that was a good review of Lewis structures. Again, if there's any issues with drawing these, please come to office hours and get some extra tips and tricks. To take a closer look at how electrons are distributed, we're going to look at electronegativity. So Linus Pauling developed the concept of electronegativity, and he developed that concept in order to explain bond polarity. So electronegativity is defined as the relative measure of the ability of an atom to attract electrons in a bond to itself. We can use electronegativity to define the ionic character of a covalent bond based on differences in electronegativity of the 2 atoms involved in the bond. So a nonpolar covalent bond between 2 identical atoms would have a 0% ionic character, whereas a complete transfer of electrons would result in a 100% ionic character. Overall, most bonds, they're neither 100% ionic or 100% covalent. Okay, the ionic character usually lies somewhere between these extremes. In general, the periodic trends in electronegativity are very similar to the trends in ionization energy. So you can see that trend overall in this periodic table here. In general, electronegativities increase as you move across the rows, and they decrease as you move down the columns of their periodic table. So similar to the ionization energies, the most electronegative elements in your periodic table, they're going to be fluorine, oxygen, nitrogen, and chlorine. And you notice that they're all in the upper right-hand corner of your periodic table. Notice electronegativity numbers don't include noble gases. Noble gases do not have electronegative values. So looking at electronegativity compared to ionization energy, these graphs right here give you an illustration of the differences in electronegativity and ionization energy. For clarification, remember ionization energy is the energy required to remove an electron. In this chart here, we're only looking at the first ionization energies. So overall, you can see electronegativity very closely follows the trend for the first ionization energies. So we use these electronegative values to help characterize the ionic character of the bond. So looking at 2 atoms, okay, it has an ionic character based on the difference in electronegativities of the 2 atoms. So although there's no clear distinction, we can make some generalizations based on the change in electronegative values. So if the change in electronegativity is greater than 2.0, the bond is considered to mostly be ionic in character. So for example, let's look at NaCl. Okay, so for Na, the electronegative value of Na is equal to 0.9. So that's for Na. The electronegative value for chlorine is equal to 3.0. So the change in electronegativity is equal to the absolute value of them subtracted together. So 0.9 minus 3.0. So the change in electronegativity for NaCl is going to be 2.1. Okay, so overall, anytime your change in electronegativity is greater than 2.0, it's usually going to be ionic. Okay. If your change in electronegativity is less than 0.4, this is mostly going to be a nonpolar covalent bond. Okay? So, if your change in electronegativity is less than 0.4, it's going to be nonpolar covalent. Okay, and then we have this spectrum in between. Okay, so going from 0.4 all the way to 2.0. And in that spectrum, it varies. It's neither ionic nor nonpolar covalent, there's a range. If we take a look at the hydrogen halides, so that's going to be HF, HCl, HBr, and HI. So the ionic character of these increases as the electronegativity of the halide increases. Okay, so if you're going from bottom to top of the halide group, then the change in electronegativity is going to increase. So the change in electronegativity for HI it's only 0.4. So this would be considered weakly polar. And sometimes we would even call it nonpolar, depending on which definition you use. Okay? And of course, this would be covalent. And then the polar covalent character increases as you keep going. So HBr, the change in electronegativity is 0.7. And for the change in electronegativity of HCl, it becomes 0.9. And the change in electronegativity for HF is 1.9. So this gives you a high polar, so it's highly polar. And it's so highly polar that it's sort of almost ionic. Okay, so you can see how the change occurs there. So this idea of polar covalent that I've been talking about, Lewis, he understood that electrons in covalent bonds were not necessarily shared equally between the two atoms. So for example, the shared pair of electrons in the bond between between hydrogen and chlorine in HCl, okay, they are more closely associated with the chlorine atom. So the electrons move towards the chlorine atom versus the hydrogen atom. And this unequal sharing of electrons in a covalent bond results in this uneven distribution of charge. So one end of the bond is slightly negative and the other end is slightly positive. And so this idea is captured in the term polar covalent bond. And so bond polarity is basically a measure of that magnitude of unequal distribution. And bond polarity is completely dependent on what those electronegative values are. So we needed a way to sort of talk about this. So because electrons in covalent bonds are more closely associated with the more electronegative atom, the end of that bond is more negative, and the less electronegative atom an atom is, that end is going to be positive. So the polar bond can be represented as a partial positive and a partial negative charge on either atom. Alternatively, Okay, we can indicate the direction of the polarity with an arrow. So sometimes we talk about these partial charges. So we write these above the different elements. And then other times we indicate it with an arrow. And so we have a positive end to the arrow and a negative end to the arrow. And remember, the degree of polarity all depends on the difference in electronegativity of the different atoms in the bond. So an important thing to keep in mind, we talk about covalent bonds and we talk about ionic bonds, but really, in reality, there's no clear distinction between the two. It's more of a gradual transition from a purely covalent to a purely ionic. So examples of covalent, polar covalent, and ionic bonds are shown here, so you can kind of see the difference. The colored bar up here at the top, okay, that's indicating the relative charge distribution from one end of the bond to the other. Okay, so if it's red, that means that that's a really high electronegative place. And if you look here, okay, here's the representative charges. Okay, so here at the 0, okay, that means the charges are completely equal, it's purely covalent. And when you have the +1 charge the -1 charge is here and the +1 charge is here, okay, that's representing a purely ionic where it's completely transferred the charge. So at one extreme here we have a completely purely covalent bond between two identical atoms, so two chlorine atoms. In this case, the bonding electron pair is shared completely equally, and the difference in charge from one end of the bond to the other is equal to 0. So we call this a nonpolar covalent bond. At the other extreme, we have a complete transfer of electrons. Okay? An electron is moving from sodium to chlorine. In this case, the difference in charge is +1 on sodium and -1 on chlorine. And this is an ionic bond. The case for the bond between these two, HCl, okay, that's going to be somewhere in between these two extremes. There's a partial positive charge on the hydrogen. So let me draw that in. So we've got a partial positive on the hydrogen, and we've got a partial negative on the chlorine. And so this is going to be your polar covalent. So putting this information to the test, you're going to have a practice problem. Go ahead and read the problem and then answer and tune back in for the answer. So to answer this problem, you're going to want to refer back to the figure that has the electronegative values for each of the atoms listed so that you can figure that out. I will show it here. Okay, so here's your table, and you're going to want to know carbon, nitrogen, oxygen, hydrogen, and is there any others? Oh yes, sulfur. Okay, so you're going to want to make a note of those values to do the rest of the problem. You also needed to know chlorine. So you're looking at these and you go about solving this by calculating the change in electronegative values for each bond. Here are those calculated electronegative values. So in the first one, you can see that the carbon-oxygen bond is more polar. And looking at both of these, okay, they're both above 0.4, but they're below 2. So these are both going to be polar, covalent. I spelled covalent wrong. Okay, for the next one, they're both 0 in their change in electronegativity, so that means that they're both nonpolar covalent. I did it again. Okay, and then the last one, NH, okay, that's going to be your more polar, And notice that you've got 0.4. So that's going to be very close to being considered nonpolar, but it does have just enough polarity where we still classify it as a polar covalent. My pen just wants to do that. Okay. Thinking about this problem, so the bonds that are including nitrogen and oxygen, you'll notice that they are more polar. Okay, so here's oxygen and here's nitrogen. Okay, which is consistent with the overall periodic trend in electronegativity. Okay, so you'll notice in this case, okay, it's carbon combining with either sulfur or oxygen. Oxygen's the more electronegative. In this case, it's hydrogen combining with either nitrogen or carbon. Nitrogen is the more electronegative. Okay, so this follows the overall electronegative trend of your periodic table. So I'm stopping our recording here, so we'll be breaking it up into 2 recordings. Alright, so far you know how to tell the difference between types of chemical bonds. You have focused on their nomenclature. That is something that's going to be kind of on you guys to learn with your worksheet, so please come to my office hours if you need any extra guidance with the nomenclature. We've worked on Lewis structures, which is also being a big part of your lab number 5 that we're doing this week, and then we've covered electronegativity. Alright, so I will see you in the next lecture.